Okay, so this is my student who used the ICESat-2 to look at the same material. I have the picture here. One of the things she was very proud of when we met is that there's a spider monkey from South America named for her family, and I looked it up on Google or on Wikipedia and found out there's also a cat named for her ancestor. Okay, so again, this was the paper, and again, this is in press in transactions in GIS. And the same story about the free global DEMs. Now, the ICESat-2, this is the table when she did her study and what's in the transactions from last year. She had 3 study areas in Brazil, California, and Virginia. She picked Brazil because she had initially done a project with me on using ICESat-2 to see what we could find about forest fire devastation in the jungle. And then when we wanted to combine the 2 papers, we couldn't find Brazil LiDAR. So we took 2 of the areas that she did here and then repeated the analysis with the same areas that we talked about in the other one. So we've got 8 different locations overall. And the source of our ICESat-2 data was from openaltimetry.org, which is, in my view, a much more GIS-friendly source of data than some of the other alternatives. So here are the locations we looked at. And the key thing to look at here, the column has the number of LiDAR 1 degree cell or 1 second cells that we could use. And the next column is the number of ICESat-2 cells. And you notice that the percentage of the cells with ICESat-2 is about 1 to no better than 2%. And that's because ICESat goes in long linear tracks. And so you get 1 cell in the 1 degree DEM that has coverage and then nothing for a long ways to either side. So here is an example from, this is El Hierro, the edge of the world in the Canary Islands. This is 1 day's worth of ICESat. ICESat comes by once a quarter. So you'll notice there are 3 somewhat widely spaced tracks, and then each of those 3 has 2 beams right virtually next to each other, but they're actually in different 1 arc second cells. And so this is what you get. There are 2 data sets. You can get the ATL-08, where you get the ellipsoidal terrain height and the canopy height. So you convert the ellipsoid to EGM 2008 ground elevation to compare with everything else. And then you add the canopy height to get the top of the canopy. So on the right profile, we see what it looks like. You have the brown, which is the ground, the green, the top of the canopy. You can clearly see the 3 different profiles. And if you look at the one on the far left, you can actually see there's a slight difference between the 2 beams of that track. And so you have these individual points. And so we interpolated the 1 second global DEM to each of these locations to come up with the height that SRTM or ALOS or Copernicus measured. We also looked at the ATL-02 data set, which is photon heights, where you get an individual measure approximately every meter along the track. So very short, but again, just along the track and then nothing on either side. So these are examples of 2 of them. The photons have with a confidence interval. But I think at this scale, again, this is pretty good relief because this is, a 1,500 meter high edge of a volcanic crater, that there's a lot of noise there. But it does allow us to sort of create a very sparse 1 second DEM with a reasonable number of points. Okay, here are actually 2 of Terra's profiles in Brazil. You can see we've got the LiDAR ground, the LiDAR canopy, and then we've got 3 of the DEMs sort of generally in between, but at places there's some pretty huge noise in the like hundreds of meters range. So there's challenges using it. So if we compare the two ICESat-2 products for the 3 areas we looked at and the 3 areas here, you'll notice, I think, that we've got a lot of air shots, a lot of ground shots, and maybe ALOS is better than the others, but I'm not sure that's worth. And the photon data is definitely noisier. For the ATL-08, they have done some processing and gotten rid of the worst of the data. Okay, so here is the same 8 test areas that we looked at. And again, we've got Slovenia, we've got the Appalachians in the US, we've got the Great Basin in the US, we've got the Canary Islands, 2 of them, El Hierro and Ecode, we've got Norway, we've got Oahu, and then we've got the Redwoods in coastal California. And again, this is the ICESat. You notice that generally Copernicus is the best. There are some areas where it's less good, and then Aster probably the worst. Okay, now when we try to normalize the point clouds, you'll see that everything is pretty noisy because in each pixel, we've only got 100 points compared to 1,000 to 10,000, and then we've got a much smaller number of cells overall. Because again, we said at best right now, ICESat-2 covers 2% or less than 2% of the 1 degree cells within the areas. And so, each one of these is a little different, and I don't want to spend a lot of time analyzing them individually, although it's kind of interesting down there in California, which is the one where in really dense redwood forest, on the bottom, the photons seem to do a good job of hitting the bottom and the top. Okay, so if we look at the ATL-08 data, we have a very similar thing compared to the other analysis with the LiDAR. Now, we also looked at the land cover. So we had the 4 or 5 of the different types of forests that we were seeing in the area, and there is some indication that the vegetation category determines how good or how bad your coverage is. Now, this is probably the most interesting. We compare the LiDAR to the ICESat-2. So on the left, we have the LiDAR, on the right, the ICESat-2. The areas are all in the same place. And again, you want to be the green and minimize the brown and the blue. And you see there is a reasonable correlation between the two. But in general, ICESat-2 has more both high and low shots. I think one of the things about ICESat-2 is it's probably designed to work much better in flat areas. And so if we had chosen flat areas for this, we might have slightly different results. But we still come up with, in both of these, that I think you can see that Copernicus is clearly the one that's doing the best job of having its elevation within what the LiDAR sees. And our assumption is that whatever the LiDAR was seeing is what was really there that the radar or the visual sensor was doing for the 1 second DEMs. So here we have the normalized point clouds, and again, 50 times more 1 second cells between the two. But the general characteristics are fairly similar. And he'll point out, when you're just doing the random sampling, if you look at BLED, which is the top left in each one, exactly where that ICESat-2 pass makes a big difference as to how much vegetation there was and how flat the area was. And so you get much more better statistics with the LiDAR. It's a smaller area. Okay, the visual comparison we went over again. The LiDAR is What we're saying is the ground truth. When we compare it with the USGS NED, they're very similar. And then Copernicus comes closest to doing that. So again, our 1 second DEM ranking, Copernicus is the best, then ALOS, SRTM and NASA DEM are in a tie, and then Aster is at the bottom. The 1 second DEMs are mostly within the canopy, defined by the lasers, whether it's the LiDAR or the ICESat, and then they're intermediate between a DSM and a DTM. There's little advantage to using the ATL 08 instead of the ATL, don't use the 2, use the 8 product. The LiDAR is better than the ICESat-2, but ICESat-2 does have global, if sparse, coverage. And with that, I'm happy to answer any questions.